This is a video of some examples of standing waves on a string. So the basic equations for standing waves on a string are that the frequencies of the normal modes of oscillation are integer multiples of the fundamental frequency, where F1 is called the fundamental frequency. And that would be in hertz. And that is the standing wave pattern that has one loop. So the string goes up and then it goes down and up and down and up and down. The length of the string we'll call L. The point where there is no motion is called a node. There must be nodes at the two attached ends, and then depending on which frequency you're looking at, there can be nodes in between. So for example, if you're doing the second harmonic, n equals 2, you'd have 2 loops, and you would have 3 nodes, 1, 2, 3. So these are the nodes. The wavelength of this wave, so in this case, if we're in this pattern of oscillation, the wavelengths lambda n is 2L over n. And so these are the wavelengths of the waves on the string that produce these normal modes. And so in this case, if n equals 2, then the wavelength is lambda 2, and that just exactly equals the length of the string. So you can see this is one wave. It goes up, down, up. That's one wave, which means one loop is half a wave. So from here to here, which is the distance between the nodes, this is half of a wavelength. And that's that's always true, the distance between nodes. Okay, so that's how the frequencies and wavelengths work. The thing that ties these two together is the speed of the waves on the string. So this is the speed of waves that are interfering on the string. And that would be in meters per second. And this would be true for each. You could put Fn if you like, for each normal mode. So assuming that by oscillating in these different modes, you don't change the tension enough to change the speed stays the same. So we also know that the speed of a wave on a string is related to the tension in the string by the formula T over mu, where T is tension in the string, which is in newtons. Mu is called the linear mass density, and that would be in kilograms per meter. Now beware, if you're given anything in grams per centimeter, you have to convert to kilograms per meter. Okay, so let's do some of these questions now. Question number 1, it's a violin string vibrating at 440 hertz, that's A, that's the note A, as its fundamental frequency. So number 1, F1 is 440 hertz. And it says, what are the frequencies of the first 4 harmonics? So that's the first one. And then, so that's n equals 1. F2 would just be twice that. And so that would be 880 hertz. And that's the second harmonic. Now this is also called the first overtone, which is a bit of a nuisance, but that's what they do. So that's the first overtone or the second harmonic. F3 would be 3 times the fundamental. And so that would be 1320 hertz. So that's called the third harmonic. And then F4, the fourth harmonic, you just multiply by 4. Okay, so that's how you get the frequencies of these higher harmonics. It'd be 1760. Okay, so that's pretty basic. So this guy would be the fourth harmonic or the third overtone. Okay, so question 2. It says a particular string resonates in 4 loops at a frequency of 240 hertz. Okay, 4 loops. So we draw 4 loops. 1, 2, 3, 4. Remember, this is just there's no string that's like up and down at the same time. This is just the maximum and minimum positions of the string as it oscillates back and forth on here. At some point, it's completely horizontal. You can't even tell. It's just passing through. But anyway, so this is F4, which is NF1. So it's 4 times the fundamental. And it says this frequency is 240 hertz. Give at least 3 other frequencies at which it will resonate. Okay, so, well, if we can get F1. F1 must be F4 over 4. And so this would be 240 divided by 4, 60 hertz. So it's fundamental to 60 hertz. So any multiple of 60 will cause this string to resonate and make a nice loud sound. Other frequencies and they'll just die out. So you could just list the first 4, I guess. F1 would be 60, F2 would be 120, F3 would be 180, and then we've got F4, it's 240. Okay, so if you were to, like if you had a frequency generator, say at the end of this string, and you're oscillating it up and down to make these normal modes of oscillation, you would, when you hit 60 hertz, you would hear this nice clear sound. Then you'd kind of hear nothing and it would be kind of a mess and it wouldn't interfere properly. Then you crank it up, crank it up, crank it up, and then suddenly you would hear this nice 120 hertz sound when you came to the 2-loop pattern and then the 3-loop pattern and so on. Okay, number 3. And this one says the speed of waves on a string is 97 meters per second. So we're given V, 97 meters per second. If the frequency of standing waves is 475 hertz, so F, now we don't know which F it is, not necessarily fundamental, but it's simply F, is 475, but we do know it's one of the normal modes. The question is, how far apart are 2 adjacent nodes? Okay, so remember V is F lambda. Lambda then for that particular mode must be V over F. And so that would be 97 over 475, which I think is 0.2. Okay, and no matter what pattern it is, the distance between nodes is half that. So it all depends how long the string is for how many nodes that we have here. But in this case, distance between nodes is lambda over 2. And so that would be 0.10 meters. Okay, that's 3. Now, number 4 is a really good question. It's one of these ratio questions, and you have quite a few of these on your assignment. We have 2 strings. Oh, this is not, this number 5, that's the ratio. Number 4, it says 2 successive overtones of a vibrating string are 280 and 350. So we have Fn is 280. And the next one, we don't know what n is, but we just know they're adjacent. So this must be n plus 1 is 350. N could be anything. It could be 6 or 7 or 8. We don't know. But we want to know what the frequency of the fundamental is. So we want to know what F1 is. Well, we know that the difference between from normal mode to normal mode, the difference is the fundamental. So the change in frequency would be Fn plus 1 minus Fn. And Fn plus 1 is n plus 1 times the fundamental. And Fn is n times the fundamental. And so this is actually proof that the consecutive normal modes are separated by the fundamental frequency. And so that's how we know the fundamental frequency is 350 minus 280 or 70 hertz. So that would be the fundamental. Okay, so beware when you're given two frequencies, they're not necessarily number one and number two. They could be any two. But if you take the difference, you're going to get the fundamental. Okay, number 5 is the ratio question I was talking about. So we've got these two strings on an instrument. It's not a violin because the strings are G and B. So I'm not sure which one it is. It's either viola or a cello or a guitar or something. But we're given the frequencies, the fundamental frequencies. So F for the G string is 392 hertz, and F for the B string is 494 hertz. Now we have all the variables we have speed, we have wavelength, we have frequency, we have tension in the string, and we have the linear mass density, which is in fact the mass over the length of the string. So we could list those as M and L or mu, it doesn't matter. What we want to do is make an equation that has all these things in it. So the equation I'm going to make is that, well, we've got two. We've got V equals the root of T over mu, or I could write that as T times the length of the string over the mass of the string. There's one equation. And we also know that this is equal to the wavelength times the frequency, because V is lambda F. Okay, now I'm going to write this out. This is true for each string independently. So I'm going to write it out as frequency of the G string times wavelength of the G string must equal the square root of the tension in the G string, length of the G string over the mass of the G string. Okay, that's equation number 1. But this is also true for the B string. Frequency of the B string, wavelength on the B string for the fundamental is the tension in the B. These are independent strings. You can, now they would tend to be the same length if they're on the same instrument, but if you put your finger down, then you're going to change the length. So see what's going on here, and mass of the B. Okay, that's number 2. Now what we don't want to have to calculate all these numbers. We're interested in ratios. So look what happens if I take equation 1 and divide the whole equation by equation 2. I will get a whole bunch of ratios. I'll get the frequencies. You just take each letter and put it in where it appears in the equation. Then we get the ratio of the wavelengths. Under the square root, we would have the ratio of the tensions, the ratio of the lengths. But now look what happens. Because the mass is on the bottom, I have to flip those over. This would be MB over MG. Okay, so those are flipped over because, look, follow the G, TG, LG over MG, and the other one's upside down. Okay, so look how many ratios we have here. This is a good equation. This is number 3. You can answer lots of problems with this equation. I've got 1, 2, 3, 4, 5 ratios. You will be told 4 and asked for the 5th. So I could tell you anything. I could say, oh, here's the ratio of the frequencies. A whole bunch of ratios are 1, like they have the same wavelength. So that would be 1. They have the same tension. The tension ratio would be 1. They have the same mass. Mass ratio would be 1. Maybe then you have to find out what the length ratio is. So in this particular question, let's see which ones are we given. So we're given the frequencies. So we're given the frequency ratios. So we have frequency of G over frequency of B. So that's given. Where do I have those numbers? Which would be, what was it, 392 over, this would be 392 over 494. Okay, so we're given that one. Make sure I got that right or wrong. G string, yep, okay. Now, so that's this one. Now, what else are we told? It says the two strings have the same length. Okay, so we're given LG over LB equals 1 because they have the same length. And then we're told they're under the same tension. Okay, so we're told TG over TB equals 1. That's 1, 2, 3 ratios. And then it says, we're asked, what is the ratio of the masses? But we need one more. Well, this one, if they're the same length and they're oscillating in this fundamental mode, the wavelengths are the same as well. So essentially you are given that the wavelength of G over the wavelength of B is also 1. That's given. And then the unknown is the mass of G over the mass of B. Okay, so now we can go back to our equation and just pop all these numbers in for each of these ratios and see what's left. And be careful, they're asking this upside down from the way I've got it in the equation, so we'll have to be careful there. Okay, so FG over FB, 392 over 494. Ratio of the wavelengths, 1 equals the square root. Go back to here. That's 1. That's 1. That will be left. So I'll have a 1 times a 1 times, now these are upside down, B over G. That's okay. We're going to flip it when we get our answer. Okay, square both sides. And we have that 392 over 494 squared must be MB over MG. Or MG, flip it, over MB is 494 over 392 squared. And I didn't have to work anything out. And that equals 1.59. The G string, this lower note tends to be a big fat string, so it's heavier. So that's 1 point. So that was A. Now we can use the same equation for B. We're just going to be told different ratios and have to work out a different ratio. So B, now it says the two strings have the same length. Okay, so LG over LB is 1. They have the same wavelength, lambda over lambda, 1. They also have the same mass per unit length, which means the masses must be the same. So MB over M, doesn't matter which way I do it, it's 1 anyways. The frequency is then due to the wave speeds. And we're asked for tension. What is the ratio of the tensions? And so, of course, we have the frequencies. We have FG over FB is the 392 over 494. So we have that. That's 1, 2, 3, 4 we have. And the unknown is the ratio of the tensions. TG over TB, except once again, they ask it upside down. That's okay. We're going to do it the way the equation says. So we go back to our equation and we have the frequencies. Whoops. FG over FB. And remember, we have the wavelengths. And in the root, we have the tensions. Everything is the right way around. G, B, G, B. But these are backwards. B, G, because it M's on the bottom. Okay. So here we go. 392 over 494 times 1 equals the square root G over B times 1 times 1. Square both sides, and you get, and then flip it, square both sides and flip it, you get TB over TG should be 0.63. So you guys can check that that works out. Okay, so that'll do it for this video.